Hi guys. Uh, I'm sorry I can't make it today and tomorrow, so that's why I've just decided to make a short and but rough video to help you guys go through the following content. Um, we are going to start our journey in chapter 4. Um, so basically, the content I'll be covered today will be involving 4A and as well as 4b. So basically in 4a, we are going to talk about the rectangular hyperbolas. There are several things I want to mention at this stage. I've cropped some of the photos from the textbook, so to indicate some of the basic features of the very first graph, which is called a hyperbolus. In general, we also call it a rectangular hyperbolus. It's got a rule of y equals 1 over x. Over here, as you can see, 1 over x is same as x to the power of negative 1. If you have already learned the exponential previously. Um, so the graph of this diagram looks like, um, it's symmetrical. I wouldn't really call it symmetrical. It's kind of like facing each other diagonally. Um, and the way we draw this graph is usually similar to the way we draw the parabola, by set up a table and you plug in a set of value of x, then you got a corresponding value of y. But as you can see, the graph of these rectangular hyperbolas is very special. It's just because it feels like these graphs stretch out in both directions. It never touch either x or y axis. Yeah. So that's where we start calling these x and y axis the isotopes. So what are the isotopes? Isotopes are the ones that um, you're getting approach to it, but never touch it, right? And for those isotopes, we also got a algebraic rule to describe it. For example, for the standard rectangular hyperbolas, we got the y-axis, which is x equal to 0, and the other hyperbolas can be described as x-axis, which is um, y equals 0 over here, right? So basically, that's the most fundamental graph we start with. These will be mainly focused on 4a in terms of the general graph. I mean, that's the most fundamental graph. In 4b of the textbook, we're going to mainly focus on another different type of graph, which is called truncus. As you can see, if you compare the function of these two, the truncus is defined as y equals 1 over x squared. If you know, the exponential rules, by flipping this power, you end up with x to the power negative 2. So basically, the way we draw the truncus is that, it's symmetrical around the y-axis, and also for this graph, you can obtain the general plotting by plugging um, a bunch of values ranging, say, for example, from -3 to +3. If you choose for x, and you get the associated values of y's, you'll be end up with this kind of a graph. Uh, Similar to rectangular hyperbolas that we have just demonstrated previously, this graph also got two isotopes, as you can see. As the graph stretch out, it kind of never touch neither x-axis or y-axis, so that's why, vertically you got one isotope, horizontally you got another one. So similarly, y-axis can be described as x equal to 0, x-axis can be described as y equals 0. With the understanding of these two fundamental graphs, we should be able to actually move on to talk about some of the advanced algebraic manipulations based on the fundamental graph. The very first thing is, there's an example that I pre-attached to the lesson plan. We need to do some algebra manipulation or transposing based on the algebra fraction. Let's have a look at the first one over here. X plus 3 over x minus 1. We need to first demonstrate that's equivalent to 4 over x minus 1 then plus 1. Yeah. How would that be possible? Well, I highly recommend at this stage, since at least there will be two different ways to do that. You can use long division if you like it, or you can actually pull x plus 3 apart into x minus 1 and plus 4, right? If I can do that, x plus 3 over x minus 1 will becomes x minus 4, sorry, x minus x plus 4 x minus 1 over x minus 1. Oh, my bad. So that's x minus 1 plus 4 over x minus 1, right? So in this case, we can further decompose this algebra fraction into two parts. The first part is, as you can see if I highlight this bit, x minus 1 over x minus 1, which is 1. Then for the second part, you got 4 over x minus 1. So that's how we just generally prove that. Then based on this, you can go ahead and draw the graph. If you compare that to the original graph of y equals 1 over x, so y equals 1 over x looks like you got x-axis, you got y-axis that looks like this. Yeah. Then if you got 1 plus 4 over x minus 1, what we can actually do over here is, since we haven't really learned the transformation pairs, we're kind of gonna go through these a little bit mechanically. Yeah. So we will highlight these two numbers over here. This one obviously will move everything up by 1 unit. So including the isotopes. This minus 1, that's minus 1, you move everything right by 1 unit. So overall, by looking at these two numbers here, you'll be able to actually figure out mechanically, let's say at this stage, the whole graph will be moved up by 1 unit, then move to the right by 1 unit. So the way I'm going to draw my graph is by, first of all, find out my new isotopes. Then I'll be drawing the graph around it. For example, the original isotope was, the vertical one was y-axis, which was x equal to 0. Then the horizontal one was y equal to 0. If I move everything to the right by 1 unit, I'm literally transform the vertical isotope 1 unit to the right. So I'll be end up with a new isotope which is also vertical, that is y equals 1. X equals 1. Then if I move everything up by 1 unit, I'll end up with a horizontal axis, which is y, horizontal isotope, which is y equals 1. Yeah. So in this case, once I found out a new isotope, I'll be able to actually bound my graph around it. So the new graph will be somehow look like this. It's still approaching to both isotopes, but it never touches both of these, right? So that's the general way we plot the graph. Let's put aside how we actually found out x or y intercepts. You can always go ahead by plug x or y equal to 0 into the equation. They can solve for x and y. But what I really want to focus at this stage is the general plot for the graph. By first of all, find out the new isotopes, and then we bound the graph to it. Second example is quite similar, except, once you get a proof down, you're going to figure out the new isotopes based on the transformation. So let's take a look at the second one together very quickly. Okay, let's put it over here. Maybe start with a new page. All right. Okay. So the second one says 2x plus 3 over x. They want us to show that that is equivalent to 1 over x plus 1 and plus 2. How do I do that? Is I can use long division if I wanted, but I can actually just pull this apart. Given that if I know 2x plus 3 can be rewritten as 2x plus 2 plus 1. Why I'm doing that is because if you pay attention to this, 2x plus 2, that is twice as big as x plus 1, isn't it? Right? So that's why the 2x plus 3 can be rewritten as 2 bracket x plus 1 and plus another one. So therefore, the overall algebra fraction can be rewritten as 2x plus 3 over x plus 1 can be rewritten as 2 bracket x plus 1 plus another one over x plus 1. Yeah. So similarly to what we did previously, you just highlight this area, divide that algebra fraction into two parts. The first part, 2x plus 1 over x plus 1, that will give you 2, right? For the second part, you still have 1. On the other side, you got 1 over x plus 1. So that's going to be 1 over x plus 1. Yeah. So by putting all these together, we prove that, okay, 2x plus 3 over x plus 1 is equivalent to 1 over x plus 2. Then based on this, we can draw the new graph. Similarly to what we did before, we can quickly find out the new isotopes. There's 2, there's plus 1, but be very careful. This plus 1 is not moving to the right by 1 unit. It's really moving everything to the left by 1 unit. And this 2 is shifting everything up by 2 units, right? So just make a mark over there, then we can quickly draw the new isotope. The original isotope for the rectangular hyperbolus is, horizontally we got y equal to 0. If you move everything up by 2 units, that will end up with y equals 2. And vertically, we got x equal to 0. If you move everything to the left by 1 unit, you end up with x equals -1. So that's the second isotope over there. Similarly to what we did previously, you just need to draw a new graph which is bounded by these two new isotopes. So that will be looks like this. Right? Notice that the orientation of the graph did not change, so that could be the quickest way that we draw it, right? Then for the third one, it's kind of similar. Let's move on to the new page and quickly do that. So the third one is a little bit difficult because it's kind of hard to rearrange it, right? So in this case, you have to play around about some manipulation about negative numbers, even involving the factorization. So that's not what I suggested. What I suggested is that I would highly recommend that if you can try long division in this way. So what I mean by this is if you go with a 3 minus 2x, you can rewrite this as -2x plus 3 because of a commutative law. Then, you just use -2x plus 3 divide by the denominator, which is x minus 2, right? Then we can start counting. What times x minus 2 will give me -2x at least. So obviously that's -2. Then if you go with -2 times by x minus 2, that should give us -2x. Negative 2 times negative 2 give me positive 4. Then 3 take away 4 should give me negative 1. There we go. The remainder is negative 1. So if I put in all these together, that implies that I can rewrite 3 minus 2x over x minus 2 is equivalent to, you can put a reminder by the end, it's just really about negative 2 minus, you bring this 1 to the numerator's position, so that's a negative 1, so that's minus 1. You can put negative sign to the very front, 1 over the same denominator, which is x over 2, right? So this is how we actually reposition these numbers by using long division. Once we get this one down, the rest will become pretty straightforward, because the graph, the way we plot the graph will be similar to what we've done for the previous two examples. First of all, if you do mechanically, everything will be moved down by 2 units, and likewise, minus 2 does not imply moving to the left, but it's moving to the right by 2 units. So therefore, the asymptotes will be horizontally will be y equals 2. Vertically, that will be x equals 2. Then the very last thing we do is to quickly bound our graph around these two newly transformed asymptotes. So that's how we generally plot a graph in general, right? All right, so that will be it for 4a. In 4b, remember the truncus we talked previously looks like this, right? So that was the truncus. We are going to use this graph to go through example 3 together. For example 3, we also got some mechanical way to solve this question. That is, once you highlight this transformed effect over here, this minus 4 really transform everything down by 4 units. However, this plus 3 does not move everything to the right by 3 units, but instead moving everything to the left by 3 units. One quick way of doing that, like what we did in the parabola, remember what we did in turning point form, right? So you just do it in a similar way by solving x plus 3 equal to 0, you get x equals negative 3. That's how we know that how to find out the new asymptote, right? So like what we did for the rectangular hyperbolas, I will also recommend to find out the new asymptote first. So the new asymptote, if you remember previously for the truncus, we got 2 asymptotes. The first one is horizontally x-axis, the second one is vertically y-axis. Namely, we got x equal to 0 for y-axis and y equal to 0 for x-axis, right? Then if you move these 2 asymptotes down, the horizontal one down by 4 units, you end up with y equals negative 4. Then the second one, if you move the vertical one to the left by 3 units, you end up with x equals negative 3 as the vertical asymptote. Since there's no horizontal reflection, the graph will stay in the same orientation, but the challenge for this question is there's a vertical transformation. So as you can see, there's a vertical reflection over here. As you multiply the entire function by negative 1, and that's going to flip the entire graph upside down to this kind of graph, right? So given that we got a new asymptote, the new graph will still bounded around it. The new graph should look like this. It's just like because of this negative 1 over here, you multiply the original function by negative 1, and that's where it's going to affect the overall shape of the graph, right? So I hope my brief explanation will kind of make sense, but at least for the rectangular hyperbolas. So please feel free to rewatch the video later on and check the lesson plans for the practice. I'll leave 4C later on Thursday for self-directed task, so that some of you, in case if you have managed to go through the exercise of 3A and a B, you can actually go ahead and to have a look at 4C. Then later on, you can have a go with it. But our primary goal is to make sure that we understand 4A and 4B first. Try your very best to complete the associated exercise before you move on to 4C. All right, thanks for watching, guys. I hope this will be helpful, and I shall see you soon.